Thanks so much, George. I may be the only card-carrying statistician in the room, so it's a privilege to be here. You might be curious to know that just last month we had our big annual American Statistical Association meetings right here in DC. There was 7,000 statisticians all there for about 5 days with 30 to 40 concurrent tracks going on. And there is activity on this front from statisticians, but if you know any, befriend them, be kind to them, and get them on your side, because I think we statisticians definitely have a role to play in this whole computational toxicology framework. I've really been pleased to collaborate with Yvonne and Fred Wright and their teams at UNC, and I think it's largely because of our relationship that we've been able to build that we've been able to come to today and work on these projects together. I'm going to focus in on the ToxCast data and the goal. What is it? There we go. Our goal is really to take in a sense, a brute force statistical approach to predicting the various endpoints from ToxCast. So we're coming to this really with no skin in the game, in a sense, as biases towards certain bioassays or even what predictors we're using. We're just viewing this as, here's some things we want to predict, and here's some things we can predict those with. We call the things we want to predict our endpoints, and our predictors in this case are the bioassay measurements that were done there in ToxCast. So we're going to try and predict those with an approach called cross-validation, and I'll go into that in a moment, which I think is critical for this kind of data. Here's the specs on the ToxCast data in case you didn't pick those up from Richard's talk. We've got 308 different chemicals. There were some duplicates running there, so we reduced it down to 308. And 75 different things we want to predict, 75 endpoints. And these range from different things like liver necrosis. You'll see a list of those in a little while. But for a lot of data mining problems, you just have one. Here we have 75. So we're having to expand our minds a little bit about how we're doing things and taking almost a more global approach to seeing how well we can predict over all 75. 615 predictors. This is somewhat small by our standards today, certainly in terms of omics data, where we could have millions of predictors, SNPs, mass spec measurements, microarrays, the next gen sequencing data now, so serving up millions of possible predictors. And we've already heard this morning about high throughput type methods where we're going to always be in this game. It certainly seems for many years to come where we will have many more predictors than we have observations to predict, the so-called wide data sets. So if you kind of view this as a little box diagram of a data set, most data miners will format their data in this way where the predictors will be the columns along with the endpoints. They're also columns in your data, and then the various observations are the rows. So in this case, in ToxCast data, we have 308 rows and 600 plus columns. Now, just to, I don't know if you saw this morning, the Netflix prize got awarded $1 million to the team from Belcore. Is everyone familiar with this contest that's been going on for a couple of years? You know the company Netflix, they're the ones that send you the movies. They set up a contest for anybody that wanted to participate. They gave them a training set and said, I want you to help predict the movie preferences of newcomers to our site, so that when you click on Netflix, they'll show you your favorite movies based on choices you've made in the past. And it was a really exciting competition. It lasted for almost a year and a half. Their target was a 10% improvement over the original benchmark that they had a year and a half ago. And there was this team from Belcore and another one that literally competed down to the very last minute when they finally shut things down. And the Belcore team is the one that won. I think they're actually doing a ceremony up in New York this morning. They got $1 million for it. So there is some money to be made in this prediction game. And just in case you're interested, they've introduced a second contest now, which is more targeted. It's another $1 million targeted towards newcomers. So they want to be able to predict your movie preferences, even if you have never gone to Netflix before. And they'll do that based on where you live, your gender, age, all these demographic information. So in one sense, for statisticians, it's just another prediction game. We didn't participate, and I kind of wish I had now. But it turned out that to kind of back up Alex's claim, the models that end up winning were in fact these ensemble methods where they took several different kinds of predictors and kind of took a weighted voting approach to get the final prediction. Now, my experience is maybe a little bit different from Alex's. I think there's actually a difference between predicting these tall data sets, which is the Netflix style, where they had way many more observations than they had predictors, versus the kind that we have here in computational toxicology, which is the opposite. Many, many more predictors than we have observations. And I'm not sure ensembles, at least in my case, we haven't seen many cases where the ensemble methods work as well, but I think that question's still an open one. Anyway, we're going to use fivefold cross-validation as our assessment tool. And the way this works is you take your data set and you hold out a certain percentage. And in the case of fivefold, we're going to hold out 20%, set those measurements aside as if we had never seen them. Take the remaining 80%, fit your favorite model to those, and generate your prediction formula, and then apply that model to the holdout set and see how well you did. And then repeat with random holdout sets. And after you do this exercise, you can get an idea of how well your method is doing. There's kind of a degree of honesty here where you're trying to really be careful not to let the test set influence what you do with your training set. And there's classic mistakes in the literature where people, even if you do something simple like, well, I'm just going to run a t-test on all my predictors first to see which ones are doing best, then I'll do my cross-validation. Well, you've already biased things because you did your t-test across the whole data set. So you have to be very careful about this introduction of bias in terms of estimating your generalization error. But I feel some kind of cross-validation like this is imperative for assessing predictive modeling tools, and that's what we'll do today. Here are 8 general classes of methods. These categories are somewhat arbitrary, happens to be the way we set them up in our software. But most of the methods you've heard of will fall into one of these categories. There are hundreds of different methods out there. We decided, we kind of honed in on a set of 84, which kind of roughly covers the space very, very loosely. And so the game we're going to play here is to take all 84 models and run fivefold cross-validation on the ToxCast data set and see how well they do. To assess our model performance, there's also some different things you can do. Most of you may have heard of the ROC curve, which applies when you have a binary outcome, which we do here. All of our endpoints are binary, 0 or 1. You can set up your ROC curve, which plots 1 minus specificity versus sensitivity, and compute the area under that. And that's a general metric for how well your classifier is doing. The bigger, the better. So a perfect classifier will have an ROC of 1 or an AUC of 1. You can also do things like average sensitivity and specificity. That's a little bit different metric. We take the straight average there in order to avoid biases potentially due to different frequencies in the data, rather than just doing, say, simple accuracy where you might be biased. If one assay gave almost all zeros, you can say, well, I'm just going to predict it's going to be 0 all the time. And you might get it correct 90% of the time just because that assay only gave 10% hits. So this is designed to combat that potential source of bias. And then one final metric is called root mean squared error. That's a more statistical type, which I tend to like because it directly measures your prediction probabilities against the truth and adds them up. So we'll look at all 3, and there are a few others. When we first got started, we asked Yvonne, said, okay, we had all these endpoints. We're like, can you narrow it down for us? Give us the four ones that you think will be most relevant to the community here. And we honed in on these 4: mouse liver tumors, mouse liver tumorigen, tumor-causing agent, rat liver tumors, and rat tumorigen. These are all in the chronic cancer category. There are other ones with developmental type endpoints, as well as the MGR category, multi-generational reproductive category. But we focused on these 4, and we did some quick cross-validation runs, and we were somewhat disappointed. In only one of the 4 cases did we get some lift above just a random prediction, and that was for the rat liver tumors category. So we scratched our heads a little bit, and you start wondering when you see results like this, well, are the data good? Did we mess up? Is this just reality? What's going on? We knew going into the game it's probably going to be tough to predict these. So we decided to To expand our analysis a little bit, we thought, well, let's go ahead and run more endpoints, and also having Alex in the room at the time, let's throw in some more predictors. So we grabbed these chemical descriptors from the software package Dragon and added those in. That's 1,200 more predictors that we threw in there on top of the 615, and we'll run our models with those as well. So we can claim we're doing QSAR now too if we want to as a side bonus. As far as the endpoints, we didn't go for all 75 just because the bottom 25 actually had fairly low frequencies. So we just focus in on the top 50 in terms of frequency. So we're now up to 50 endpoints and roughly 1,800 predictors. And now for some results. This is a graph on the y-axis. We're plotting area under the curve as our performance metric. And along the bottom, the x-axis, are all the different endpoints. For each endpoint, we're showing a box plot of all the different AUC values that we got from the different cross-validation runs. So you can get a feel for the distribution of those values. Now, this is a case where we decided to use only the 615 bioassay predictors. And you can see the different endpoints there. The 0.5 line is kind of the random line. So in fact, we did find a few endpoints where we were getting an AUC up around 0.7 on average. Things tailed off from there. Now, next I'm going to show you what happens when we throw in the extra 1,200 predictors. And boom, we got quite a bit of uplift on several of the endpoints, especially that first one, which if you turn your head sideways and squint really hard, it's cholinesterase inhibition for rat. And that one jumped all the way up above 0.9. So that one was quite unusual, we thought, in terms of all the endpoints. We still had several up around 0.7, and then as you can see, they kind of tail off from there. But we feel this kind of analysis right here is nice for a kind of a benchmark type thing where everyone can get a feel for how difficult is this problem going to be in terms of prediction. And then as we get new bioassays, or we're going to hear in subsequent talks, maybe incorporating more advanced biological or pathway knowledge, either bottom up or top down, can we get some improvements on these straightforward statistical approaches? Here's the same plot for average of sensitivity specificity with bioassay predictors only. And then also the uplift we get when we throw in the chemical predictors. So this is a slightly different metric, perhaps more intuitive in that we're just looking at counts of how many times we got it correct or incorrect depending on the truth. And you can see fairly similar story. And dittos for root mean squared error. Now this metric is the reverse, and that smaller is better. So the endpoints are sorted in the opposite. You see the graph going the other way. But again, similar story. The values tended to creep down as when we threw in the chemical predictors. We were curious to drill down a little bit more on this, and just for sake of time, I won't belabor this, but we did find in several cases that we also tried some cases where we did chemical only, and it turned out, at least for this case, that it really was most of these chemical descriptors that were driving the predictors. And you can do post-processing analyses, like looking at which predictors got chosen most often. Most of the methods that we use, we had to do some kind of pre-screening up front. You can't just throw all 1,800 in. You have to kind of whittle them down by some criterion within the cross-validation loop. And so you can build up frequencies of importance. And I won't show you those today, but that'll be some things we'll be exploring in the future. Oh, we were also curious about which methods might be doing better. That's always, everyone asks, well, what predictive modeling method should I use? And I think the jury's still out. But it does seem that a couple of these methods, in particular, partial least squares and the tree-based methods, seem to do a little bit better on average. And we'll see it may be that for computational toxicology, these are the methods that tend to do better. We don't know quite yet. Which I think it's important up front to try several different ones just to see, because you never really know until you try. Okay, for the last few minutes here, I want to talk about this concept of learning curves. This learning curves are a vehicle that we can use to help us decide whether or not we have enough samples. Now this is you probably all in your Stat 101, you remember doing your sample size and power calculations. Well, it turns out in a predictive modeling context, those don't apply. And that's also a common mistake. I've actually got papers rejected because reviewers didn't realize the distinction here. But those classical power and sample size methods really don't apply to predictive modeling contexts. They're appropriate for classical hypothesis testing. So we need some other technique for getting us a feel for how many samples we need, or do we need more. The methods aren't as clear cut as those, but they can be quite informative. So what we do with learning curves is we intentionally reduce the size of our data and then rerun our cross-validation exercise and then see how our performance degrades as we get smaller. We get a curve, and then we can kind of extrapolate beyond that to see whether are we really improving quickly or are things flattening out. So for illustration, I wanted to show you just a few learning curves for two of the endpoints shown there in the last bullet, as well as I'll just reduce things down to two of our performance criteria, AUC and RMSE, and there's also just 5 best models, just to keep things a little bit simpler. This is the one for the rat cholinesterase, or cholinesterase inhibition. Remember, this is the one that we did really well on, and you can see the learning curves going up around 0.9 for AUC. You also see how they're starting to flatten out. So that's an indication that more chemicals may not help us in terms of improving things, just because we're kind of peaked out on how well we're learning, at least with this outcome. Some of that is due from the fact that we're already up around above the 0.9. There's not much more to go. And so I think drawing learning curves like this for different models can help inform us as far as, are we there yet, or do we need to go further? Now this one here is more interesting. This is for mouse liver necrosis. You can see it's also somewhat flat, but on the other hand, you can see a subtle slope going up as we go from left to right. That's indication that more chemicals probably will help. And I think it would be in support of the ToxCast phase 2, where we're looking to do quite a few more chemicals and boost and just get a much cleaner feel for the space. With only 308 chemicals, we're probably only in a very narrow region of the entire space. And these are all pesticides to boot. So I think this is some evidence. And plus, we're just hanging around 0.6. There's some hope that we could do better than that as we get better with our predictions. Same curves now for RMSE. Again, cholinesterase inhibition, kind of bottoming out there around 0.25 on that scale. And similar story for the liver necrosis outcome, kind of going down. There is a chance maybe, and we won't know until we get more, maybe that thing really is flattening out, and this is just an outcome that's going to be very difficult to predict. That could be reality, and we may have to face that. But right now, you kind of see the general trend there going down, and I'd be supportive of certainly getting more data. Statisticians always want to get more data. So conclusions, still tentative, but I think one thing for sure we saw was that the chemical predictors helped a lot. And so it's certainly in this kind of game here, I think it would be important to go ahead and include those. They're fairly easy to come by, and just a matter of throwing in extra ones in your model. So if any kind of predictions like this, we would definitely recommend including those in addition to the biological assays, as well as going ahead and run some learning curves. Everything I showed you today can usually be run in a few hours on standard hardware. And software is readily available from a number of places. So I think there's no excuse for doing some of this computational work up front. And the question that had been raised earlier, where do we start? Maybe some computations online with online data or data that you already have would be a great place to start to get a feel for what you have and where you should go from there. So work is ongoing, and we hope in future sessions to report on importance of various variables and outcomes, as well as getting at this idea of interactions, which we know there's a lot of interactions going on in the data. Some of the methods like the trees do tease those out to a certain degree, but you can get fancier with your modeling in terms of doing products of predictors or certain combinations that get at key interactions. So we're hoping to be able to tease those out too, even though we're using a straight statistical approach. So I'd like to thank you for your attention.
Thanks so much. Again, we have time for a question or two. Alex?
Russ, I just looked at how dispersed the accuracy is. And I'm wondering if this is something that you observe commonly in other data sets, or is it something that's specific? It's very large variation in five-fold cross-validation.
Yeah, I'd say it's fairly typical compared to the different ones we've run. can just take AUC there. So he's referring to the height of most of those box plots. You can see for some of the endpoints, they are tighter. So a lot of it depends on the endpoint. And fivefold too, you will see a difference. Like if you do tenfold, where you only leave out 10%, things will tighten down because it's a little bit easier prediction problem. So it's somewhat a function of the fivefold, but it is indicative that these outcomes, a lot of them are difficult to predict, given these predictors.
Yeah, couple of questions. The predictors that you're using obviously have different variance structures because they're coming from experimental data sets that have different sample sizes, different signal to noise ratios to them. Did you consider any of that in the overall analysis you're looking at in terms of the noise from that data and the noise of the signal you're looking at here?
It would be difficult, and there is a big issue about how do you, this is a case where it's not obvious how to even construct the predictors. A lot of them are derived values from dose response curves. There's a big decision about whether you discretize them. A lot of folks will actually even convert the predictors into zeros and ones. We didn't do that. We left them on, at least on the log scale, which usually seems to make more sense to log transform the measurements. And in a sense, we're trusting, and I know Richard Judson's team and others, they put a lot of time into coming out with good summary measures from the assays. Not to say that perhaps there could be better summaries, but in a sense we're trusting that the effort they put into processing their dose response curves was well spent, and that we have a fairly accurate assessment of what that assay did on that endpoint.
The other question, and maybe you can't answer it, but someone else might be able to answer it later, has to do with the nature of the chemicals that were used in ToxCast. Since they're pesticides predominantly, or pesticide inerts, is that correct, Richard?
No, they're all actives.
They're all actives. Almost all actives. So they tend to be neurologically active. That seems to be one of the major cholinesterase inhibitors. Which means the subset you're finding is not surprising, actually.
Okay, that's good to know.
Yeah, that was my same question because, I'm trying to understand what you're trying to validate because I'm wondering whether we have some circular reasoning going on because you've got lots of pesticides, you've got fungicide, rodenticide, a bunch of things, some of which herbicides, some of which are active, some of which are not, some we don't know. And then you've got organophosphates, which is a subclass, and carbamates, of which EPA Office of Pesticides program knows what the mode of action is, so they ask specifically for cholinesterase data, only on those chemicals. So your data is going to be really clean.
All of those chemicals we have cholinesterase.
You don't have cholinesterase data on all pesticides.
On all of the ones you say is
No, no, because we know that data set. we know that data set, and we know that. Well, Tina, you're the director of OPPHED. Right. Well, you mostly have cholinesterase on organophosphates and carbamates, right? That's what you have the data call in on, and the most recent. Yeah. So you've got some reason already built in that I would say if you didn't get this hit, then we really had a problem. But it doesn't give me confidence that the system is working because that's the only thing that really stands out. So I also wanted to extend this to, I was interested in the papers that you guys had online for the committee, and one of them was a case study with arsenic. And again, I started wondering, is this sort of a self-fulfilling method of validation where you already kind of know a lot of data, you have hypotheses that then lead people to do data mechanistically, and so then when they mine the data, they're surprised that they see these connections, but that's because the research has been built on that. And what we want to know is whether we can use this to predict something where we don't know anything. But all we're finding are those things that are really well studied, and we know the mode of action, and then we're using that to say, oh, we can use this then for everything else, and that makes me nervous. So I wanted to ask you to.
Yeah, I could just say, since we were being completely honest in that like the 20% that we set aside up front, we pretended like we didn't even know those chemicals existed. We built a model on the other 80% and then predicted those. And then we do happen to know the truth, so then we can see how well we did. So in that sense, we were. I don't think now. In a way, your point is a bigger one in that the whole data set, in a sense, may be kind of rigged.